Welcome to Maths Function with Sitsabe Sumsana. Thank you for joining in. Please subscribe, like, share. Today we are looking at Newton's laws of motion, the most famous Newton. We are going to look at the first Newton law, the second, and the third with you guys, elaborating them, making them, or referring them to practical daily experiences that we see every day, trying to understand them with you. So let's just dive in. The Newton first law of motion. An object will continue a state of rest or uniform velocity unless a non-zero force acts upon it. What Newton really meant here, he meant that if you could put your book on the table, it's going to stay there forever unless someone take it. So you know now, if you don't find your thing where you put it, just know somebody took it. That is according to Newton. So you have a right to fight with whoever in a room in that case. But then you should ask yourself, why do you have to find your book wherever you put it on? You always going to find your book if no one stole it where you put it because of my favorite forces, of which you know it's mg versus normal. These are things that are responsible for keeping your book wherever you put it, or these are things that are responsible for keeping your stuff exactly where they are. Like how they do this magic. There is always mg, a weight of an object that you just put on your table, your book. It's also help on keeping it where it is, and the surface that you put it on, it's also help on keeping it where it is again. Because of these forces or net force acting on this book of yours are equal, its mass and the normal force acted by a surface on it are equal. That helps on keeping it there forever unless you come and take it or someone steal it for you. So what I just said now, I said that the total forces acting on your book help keeping your book together only if they sum up to zero. So if only simple things, how can I say this? If all forces that are trying to take your book away from you are equal to all forces that are trying to keep your book from you, then your book will going to stay there forever. Like I just said, the normal the mg, the weight of the book, is trying to keep your book there on the surface, but the surface is trying to take it away from the surface. Because of these two forces that are fighting or battling against each other, they are equal. Your book just stay there because it just doesn't know who to follow, because the mg is saying like stay down on the floor and the normal is saying like yay go and fly, and your book get confused and stay there forever. That hard Newton meant. So far I've said a relationship that all forces acting on an object, they should be summing up to zero for your object to stay there, and also the acceleration of your object should be zero again. This should be square here, zero. So these are all things that are responsible for keeping your stuff. So if you don't find your stuff there, it means that the net force act on them wasn't equal, or maybe there was too many forces for G to keep them. Let me say you put your what? You put your earth, whatever you put it, an object that is equal to a mass of earth, it's going to stay there. Why it stays there? Because no one has enough force to take it away from where it is. So if you put big objects, they are more likely to stay. More like you could put your pen on a desk, it's going to disappear in some time. Why disappear? Someone has power to fight against its mg. What is exactly mg? I should mention it's mass times gravity. So let me say your pen is 2 grams, then it's going to, let me say 1 kg. Your pen, to make it simple, your pen is 1 kg times 9,8. Then this is the force that you need to encounter, to fight with, to take for someone to steal your pen. I hope we were clear. Now we are heading to the second one, the second Newton law of motion. Here Newton said when a net force is applied on an or to an object of mass, it will accelerate in the direction of a net force, and the acceleration is directly proportional to the net force and inversely proportional to to the mass of an object. What really this means? It means that if you could put your book again on the table, if you could put your book on a table and you decide to push it this way, it's going to accelerate or move this way. Simple. You can't be pushing it this way, it's going to move this way. That's what Newton said. He said in the direction of a net force here. But then he lately mentioned some relationships. He said that the acceleration is directly proportional to the net force. So then I was like, okay. I was so happy that Newton said if I push an object, this direction is going to move that direction. So if you could give me maybe a car, maybe a car, I was saying, if you could give me a car to push, the car is just going to move this direction. I was so happy that I could push anything on this earth and it's going to move. And he said something, and he said the acceleration is directly proportional to the force of Newton. And he's now meant that for an object to move, it also depends on a force that you put in. So you can't just tell your little baby to go and push your car because the force that is going to exert, uh, he has legal force. He has legal force. So going to be an acceleration. The acceleration is going to be legal. So he then represented this in a mathematical expression that says force net is uh, inversely or directly proportional to acceleration. Then that is not all what he said. He also mentioned some relation again regarding Newton's second law. He said that, okay, he mentioned that force is directly proportional to acceleration, and he said something else. He said and inversely proportional to a of mass of an object. Oh, let me just write it down. Maybe it's going to make sense. I'm really confused. And then this, and he said, force, net force, and oh, it said acceleration. Now, inversely proportional to what? To a mass. Okay, now it makes sense. He said that you can't just push your car fast as you could push your toy car. Oh, now I can get it. So what Newton said, he said that if you happen to have a toy car, both of them, you happen to have a toy car and a car, you can expect to be able to push them to a very same acceleration. Why that is so? Because they have different mass. If this one has mass m and this one maybe have 3 mass, or maybe yes, three mass because it's a real car. So he said he also mentioned that how much your car will speed depend on how much the car is, or maybe say the object in this case, because he keep on calling my cars objects. I don't know why, but yes. So now I have two relations that I got from my Newton second law. He said a force that you put in is going to equal to an acceleration that you get, but in the direction of a force, or a net force, should I say. All forces acting on that object, or maybe should I say on that car. Okay, and he also mentioned something. He said that an acceleration is inversely proportional to the mass of an object. And then Newton's made the third law again after bringing me so much confusion, and then made the third one. What he said here, he said when an object A exerts a force on object B simultaneously exerts a force of opposite direction, but those forces should be of equal magnitude. Okay, now I understand Newton. Going back to my book problem. You put your book here. Okay, you have your book on the table. He said when object A, okay, this is my table. This is my table, guys. He is now saying when object A exert a force on object B simultaneously exert a force of equal magnitude but opposite direction as object A did. Oh, this is what keep my books on the table. As just equal forces of different magnitudes, as Newton said on the third law, that are exactly equal and they just battle together forever, and my books stay there. What are these forces? Now you should know. Here, normal force is battling against mg, the weight of the book, because the book is exerting a force of its weight on the table is exerting a force on a book on opposite direction. These forces are equal. He meant to say force when force A on B, if this one exerts this a force to this, and it's a reaction. This one will do the same, will get mad and like, why are you pushing me? And decide to push back and be on A. But then he said something different because it's now of negative direction. You know, when people are fighting, let me say these two buddies of mine are fighting. My friend normally fights. So these are them. I won't mention their name. This one will push this one like this, and this one will push this one like this. Opposite direction. Like they keep pushing, pushing. It's that is Newton law. Like literally we see all these Newton laws on our daily life. So try spotting them out and drop them in comment. And I see this and relates with this law of Newton. Thank you for watching. This is Sitabiso from Function Maths. Subscribe, hit the thumbs up, comment and share for more content.